I feel trapped a bit here. Good. Shall we start? How is everyone? We can almost do this interactively. Now, it would be lovely to claim that there's masses online, but I started a bit late. They'll come. Let me briefly remind you where we left off last time. We talked about this AHO-CORSIC algorithm. We're in the overall context of string matching. The motivating problem was the read mapping problem, which is the standard application. If people do whole genome sequencing these days, they often don't want to assemble the genome as one long string, or as one string per chromosome anyways, but rather find where do those reads map to the reference genome and where do they differ. As a starting point, I said, let's first ignore that these matches are usually not exact matches, but rather have some errors. And I promise we'll come back to this at the end of today for sure, that you can use the exact matching part to also learn something about the part we care more about, where you have some small errors, but most of the string matches. And in preparation for this, we looked at KMP for finding a single pattern in a long text, and AHO-CORSIC for finding a whole collection of patterns simultaneously in a long text by reading the text only once and finding all occurrences of any of the patterns. And in a way, this was starting from a try that we turned into an automaton by adding various edges, in particular the failure links and the output links for not missing an occurrences that's a substring of some other string. And you'll have a bit of practice on the current sheet to at least do this once on an example. Now, this is already a lot more practical to do for the read mapping scenario, because we can at least take a whole collection of reads in one go and then read through the text once. We still have to do it for all the batches. Main memory will be not enough to hold the entire data set of reads in one big AHO-CORSIC automaton. There's too many of them, but with maybe a few hundred batches you can get by, and so you would read the genome a few hundred times. It's not great, but it's the best we've had so far. At least it's realistic to do this on a normal computer without going distributed. In the second part of the string matching unit, we will start looking at inexact matches, which is the biological more important case, where we're finding the occurrence of a pattern in a string, but it doesn't exactly match. And what this means, we already discussed a bit that there's various levels of what kind of errors we can allow. I've just recapped that we had KMP, AHO-CORSIC, different algorithms for finding perfectly equal matches. And again, we'll take a step back from AHO-CORSIC and now focus on a single pattern first. And you'll see the problem is juicy enough even in this restricted scenario. For the first round, let's look at alignment-based matching. So the most general version of what it could mean to match not exactly. And I will call this the gold standard of inexact string matching or of read alignment, in that it's the most precise kind of criterion for how good a match is. It misses the fewest sensible matches. So you can think of it as an alignment, as we've done in previous units, of the entire pattern and a substring of the text that we're free to choose. You'll remember what this was called, either a semi-local or a fitting alignment. We had a slide, that's the exact slide from back then. So we already know how to do this. It's a variation of the dynamic programming algorithm we've seen for alignments back then. And essentially we need this dynamic programming algorithm, the way it's written here, I don't know if it's a bit too small. You need the entire matrix even for at the end just picking the best column. So even if we're at the best cell, even if we're just interested in the score, we would have to keep the entire matrix in memory for this version. So at least if you're using this gold standard way of doing matching or finding matches in a text, you would at least want to slightly improve on this. Also, the running time will essentially remain at n times m. This is hard to beat. We discussed a bit. Okay, we can shave off logarithmic factors, but we discussed in the same context of these exhaustive tabulation techniques. We also discussed this conditional lower bound on general eddy distance problems. So one thing we can do is if okay, I prime is used before it's introduced. Let me introduce it first. The fitting alignment aligns the pattern in its entirety with some subset of some substring of the text. I don't know, just for the avoidance of doubt, let's try it. So I'm ignoring this part up front, but then here maybe I can spread, I can have an insertion, and I can mismatches, and so on. I'm ignoring the prefix and suffix of t for free, but then in between I have to use all of the characters of p, and I have to pay the general score for matches, mismatches, gaps. We don't do affine gaps here. I think that's not the problem. You could generalize to that if you wanted, but let's not do that here. We can slightly rewrite the recursion, and the difference from the original one is here I'm allowing at every point to start a new alignment. That's why this red is 0 if should this be at, okay, it's the other way around. Okay, annoying. Let's look at this one. I swapped the roles of A and B. Here, I wanted T to be the string that's horizontal, and P is the one that's vertical. T is here, and P is here. In the other chapter, I had the matrices were taller than white. So whenever I'm at the beginning of the pattern, so I'm looking at one of these cells up here, I'm allowed to start it from scratch, and that means ignoring the prefix of T up to this point. Whereas if I'm in this first column, I have to pay for getting this prefix of P out of nowhere. That's explaining these two columns. Now, the previous version, even though it's shifted, would have had the ending of the alignment in any of these cells in the last row. And then the last step would have been pick the best cell in the last row. Instead, let's reformulate the problem slightly so that we keep the best score while we shift right, so that the final answer will always be in this bottom right cell. And what we have to do for this is, for this case, where we go, we only do this in the last row. Otherwise, this is 1, and we add a gap. We're here in the cell ij, and now we're going from the left, right? It's this step going, which is deletion in T. I'm skipping a character, or I'm going over a character in T, but nothing happens in P. A deletion in general costs G for the gap cost, but if I'm already at the end of the pattern, I can do it for free. And with that, I'll have, at some point, some cell here in the lowest row will have the best possible score. And from then on, it'll stay the same as I'm going further right. Then at least I don't need to keep the whole matrix for just computing the best score. And that's the prerequisite for doing the space-efficient alignments we've discussed in Unit 3, I think it was. The rest is the same, so we can still need the same time complexity, but for the space we can improve. First of all, to just compute the score, we only need the last columns, or maybe one column might be enough if you override cleverly, and you can do it with 2 columns for sure. And you could try to use the same divide and conquer algorithm to also construct the alignment from this. Remember, this was the finding the best middle point. I'm not going to go into this detail again. The point is that the time will stay at n times m, and that's already too much. We don't really want to spend that. Okay. You don't even need to do this here, clever. You can augment the dynamic program to store when was the last time you used this 0 rule. If you store the starting point of the alignment, which is the value of I at this point, in a second table, then you can just read out that second component, and that's going to tell you for every score what was the starting point of the alignment, or what was the prefix of t that you ignored for free. That's a nifty little optimization that you can do here. So even without constructing the alignment, you can find all the occurrences that have, or you can find the starting index of the best occurrence. I think you only get the one occurrence if you throw away the table. You could collect them all, I guess. You can play further tweaks to this. Maybe it's a fun exercise problem. But really the point here should have been for our application, if we were to do this for every reading through the entire, the product of the genome and the reads, that's way too much. But it seems, unless we're compromising on one end, we're stuck with this running time, unless this lower bound from alignments fails. So it seems hard to improve on this without making some compromise. And there's 2 kinds of compromises that we'll look at. For the first kind of compromise, we'll go away from alignments and instead look just at mismatches. And the subsection doesn't have that in the name because it's titled after the technique that we'll learn about. Some people might know this. Here I'll just first use it, and then we'll see how to build the data structure that's behind this later. So to simplify the problem, let's just look at the minimal Hamming distance instead of something like edit distance. So we go away from alignments with insertions and deletions and to alignments that only allow matches and mismatches. That makes the problem a good deal easier because for every starting position in the text, there's a single unique way how you could match the pattern against this. That was not the case for alignments. Right? So for every starting index, there's exactly this one length m substring for t that can be relevant. Now you can ask this problem, you can ask in 2 different ways. One would be you're only interested in finding one match with the minimal Hamming distance among all possible matches. Or you could say I'm supplying a threshold and I want to see all matches where the Hamming distance is below the threshold. I think what I'm claiming here is basically true for both versions. This is an open problem. We don't really know what the best time is to solve this in the general case of having no pre-processing done on either of the 2 strings. There's very sophisticated algorithms that try to improve on this. I'm not going to explain these in more detail. The tricky bit is that for exact matches, you can somehow study how the pattern self-overlaps and then conclude from no match in a certain position that there's not going to be a match very close. Because there can only be a match very close if some part of the pattern that you've just looked at this point matches the shifted pattern. That's exactly what we used in KMP. That there has to be a certain minimum number of characters you shift the pattern before it even makes sense to check for another match. Now, if you do matches with mismatches, or this is the K mismatch matching, if you do matches with Hamming distance, that's no longer so clear, right? It could be that you don't have a current match here, but there's a couple of characters where you don't know because the text might differ. And then it's much less clear how much to shift further. And so there's some fairly sophisticated studies about what you can still do in this case to shift the pattern more forward. But I guess it's fair to say it's still open, and there's nothing that comes close to linear time. All these methods are still involving at least the threshold for the Hamming distance you're supplying. What can we do? Let's start simple. So again, I did this in my undergrad lectures all the time. You're not required to need to know this part. This is pointers for further interest. The material for our exam is what I actually explained to you, or what we cover in the tutorials, but not these extra things. What can we do? If I give a certain position in the text, I can compare character by character with my pattern and see if the number of mismatches I get is below a certain threshold. So for example, if I have a threshold of k mismatches and my text and my pattern, I can do the brute force string matching algorithm that tries every possible position. And instead of checking that all characters match, I'm just counting how many don't and skipping ahead if there's too many. So I go through all the starting positions in the text and all the characters in the pattern. If the appropriate characters don't match, I count that mismatch. If I reach my threshold before I'm done, I don't continue. Whereas if I leave the loop without having seen too many mismatches, then that was an inexact match, and I'm returning this one. Instead of stopping here, you could collect them all and or keep going and return all of them. For the brute force algorithm, the running time is the same. Or the worst case running time is the same. So that's not too surprising that something like this is possible. But let me point out again that this is not possible in this way for alignments. Because here we're really relying on the fact that you can check this single potential matching substring of T. That makes this so easy here. It could also easily be parallelized, as it has a few good properties. Doesn't need extra space, but if we're still in the same theta class as for the alignment-based methods. And I claimed that it's too slow, so it still is too slow. In particular, it doesn't even depend on this parameter k. Now, we'll see soon algorithms that involve k. The point where this is interesting is that both n and m are not so small in practice. N is big for sure, that's the genome, and m might be a single read where it's not so big, but we want to do this for a whole bunch of reads. So the total length of all the reads is even longer than the genome. But k, the number of mismatched characters that we would allow to still count it as a sensible match, that's going to stay small. Maybe a handful or so. Or for the SNPs, just one. So it would be cool if the algorithm somehow sped up with small k, but this one doesn't. How can we do this? We're going to use a magic ingredient that for now I'm just going to show you as a definition, and it'll take us a bit of time over the next week and maybe after the break to establish how this works internally. That's the longest common extension data structure. It does the following feat for us. We're given a string, and then we pre-process, we read that string and build a data structure so that after we have done this pre-processing, we can answer LCE queries, which means longest common extension queries, where you're given the text somehow, and the input to the LCE query are 2 positions in the text. And the output of the LCE query is the number of characters you can read from I and j to the right that are the same. And it should be the maximal, so the next one is different. So this length, that's L, the number of characters before the first mismatch. That's what's written here formally. Now, maybe before we continue, how could you do this without much thinking? Whenever you introduce a problem or a definition like this, what's an easy thing you could do? For all of these data structure problems, there's two extreme solutions that you should always try just to see how bad they are. One option is you do nothing up front and you do all the work whenever someone asks you to do the work. That's the lazy approach. No pre-processing, but whenever someone asks you for an LCE query, the only thing you can do is start at the position I and j and read from there to the right until you fail. So the running time for that is essentially the answer of the LCE query itself. It's cheap if that's short, but in the worst case, it's essentially linear. So clearly that's not so useful. That's essentially what the brute force algorithm is already doing. The other extreme approach is pre-compute everything. That's the overly eager approach. We'll worry about the pre-processing in a moment. If you store it in a clever way, say in a 2D array, then the query now just is a lookup, read a table entry, and return the number. But we have to fill this huge table. And at the very least, it's going to take constant time per entry that we write, because we have to keep all that information around. So first of all, it's quadratic space because of the table. I and j range over the whole length of the text. And the pre-processing has to at least fill this, so it has to have at least this as time as well. And unless you get creative and inventive, it's going to be worse than n squared time. So clearly that solution is not so enticing, because any quadratic algorithm on a genome-sized data set is not going to finish. Or you have to work extremely hard to make that viable. Now, the black box that I'm not going to tell you for now what it looks like internally can do a linear time pre-processing using linear space and still find the LCEs in constant time. So it is strictly better than either of these extreme solutions in that it keeps the best query time and almost, I mean, the pre-processing time was 0 for the lazy approach. That's maybe hard to beat. But the space still needs to store the string. So you could say it's linear in the same way. And this data structure eventually does the best of both worlds without any compromise. So we'll ultimately see what this works like. But for now, let's just treat it as a black box result and see what we can use from this. So after linear time pre-processing, in terms of time and space, we can find longest common extensions in constant time each. Okay. And with that, we can build what's called the kangaroo algorithm, because it jumps in various places. I'll show it briefly. There's something we need. LCE, as I defined it, is on a single string. So there's one text, and I can have two positions in that text. And then I can say how many characters are common from there on. If you think about the brute force algorithm for this inexact string matching, we really can't do anything about the mismatching part. But if I have several characters that match, I could use an LCE query to jump over those. That's what we're going to do. That's what the kangaroo jumps are. But for that, we need one position in the text and one position in the pattern, and do LCE queries across the two strings. And so at first, you may wonder how that can work, but you can build a single string so that it works. Essentially, just concatenate the two, but it's smart to put some some new characters in between that mark the end of either of the strings, so that no longest common extension will ever run out of T into P. That would potentially be a worry if you're close to the end of T and at some point in P you may use an extension that uses the first characters of P again. If you put a dollar that doesn't match any character in P, then you're safe that this doesn't happen. So we can completely ignore in the construction of LCE data structures when we get to it in the future that oftentimes you want to apply it to a set of strings, not a single string. You can always do this reduction step, and then the same algorithm works. So with that, we get to this kangaroo algorithm, which is really the brute force algorithm we've just seen, except that it jumps over the matching parts. So much of the structure looks similar, but here we first jump in from the two positions for as many characters as we can. And we increment by that many characters. And I'm already adding here +1 because I don't have to check the next character. It has to be a mismatch by definition. So I can directly jump over this and count it. And so again, if I run out of budget for the mismatches, then it would probably be useful to have k as a parameter here. If I run out of mismatch budget before I'm done with the pattern, then that's not a match and I have to continue. Otherwise, I can return this. The time for this is whatever I need for the pre-processing for this longest common extension data structure, and then a loop that runs n times and a loop that runs at most k times. So it's overall running time n times k for the matching part. That sounds not so far away from n times m, but remember that k is much smaller than m. This is the number of mismatches, so maybe a handful, whereas m was hundreds for sure. And this is indeed a useful method if k is indeed small. This is it's not the worst approach. Of course, what I'm hiding here is the complexity of building this longest common extension data structure. The promise will eventually come out true that it is in linear time to build this, but it's not for free. So in particular, if you look at it from this black box approach, it's not clear how much we can reuse pre-processing steps. At least the way we formulated it, you have to pre-process the entire genome and each read in each step. That sounds very expensive, but we can do this for several patterns. So in a way, it's not an actual problem, but you have to look into the box a bit. Or what you can do at this level is just extend this with all the patterns that you want to process in one go. Then you can make this work. Okay. The external, this tool I'm using has the tendency that it doesn't extend more PDF pages. If you add later to the slides, then you have to open them again. But nothing for you to worry about. That's as much as we can easily do for these mismatch problems. The last thing I want to look at again is this promised reduction from exact matching to having small number of mismatches. And in particular, we'll revisit these SNPs, these single nucleotide polymorphisms. But the construction is indeed a bit more general. So in a way, you could say this kangaroo algorithm is fine if it wasn't for this overhead of pre-processing. And indeed, it looks simple from the way I presented it, but you have to kind of take the black box construction into account if you judge simplicity. For very small k, we can do another trick that doesn't have strong guarantees in the worst case, but seems for bioinformatics data to work reasonably well or very well. That's the following observation. If you have a pattern and it's supposed to match some position in the text with at most k mismatches, then let's draw this so it's immediately clear. That's my text. The text continues, but I'm doing mismatches, so all that counts is some specific starting position in the text. Now, let's say k is 3. So there's some mismatches here. I don't know where they are. But the statement says, if that's all, then there must be some reasonably large portion of the pattern and text that match exactly. And that's, for example, here, all of these are equal. Maybe there's some more outside. What's the worst case for this? Well, if you balance out the mismatch parts precisely at regularly spaced intervals, then you get this bound. Or more precisely, let's draw it for a concrete example. Let's do the very extreme case first. That's how you can check the corner cases. Say if k is 1 and m is 3. The worst that can happen is that this is the mismatched character. But then I'm supposed to still have at least one character that I match. And if you insert that, that's what t comes out to. 3/2 rounded down. In a larger example, say, pick characters like this. I could probably, for the worst case, append more things, but maybe we don't. Then let's count. So that's 3, 6, 9. And k is 3. Now the bound says I'm supposed to have at least 9 divided 4, rounded down is just 2. And indeed, I have 2 characters that are matching. I could have more, right? If these are somehow more clumped together, the mismatched parts, the red crosses, then I might have a longer stretch where the pattern and the text match exactly, but I'm guaranteed at least t characters, consecutive characters match. Clear? It's easy kind of pigeonhole argument. These matches have to go somewhere, and you get the shortest fragments if the mismatches are as evenly spread as possible. And that gives you this one. So we can use this observation by breaking our pattern into k+1 substrings, each of length t. And if there's something left over, you make the last one a bit longer. That doesn't matter. All that matters is that if I'm finding exact occurrences for these fragments, there's k+1 of them. So if there's an occurrence where this pattern occurs with at most k mismatches, these k mismatches can only kill k out of these patterns, or these sub-patterns. There must be one left. And whichever you pick, it has length at least t. Okay, simple approach. And so you can use whatever algorithm from our section about exact matches to find these smaller patterns. And the occurrences where they occur, let's call those the seeds of a potential match. And then you can try to extend this. For example, if this is the portion of the text and you found that this fragment matches exactly, then you know that the pattern continues to the left and right a little bit. So you just compare the other characters and count how many mismatches you have. That's easy to do. Now, the hope is that you don't have too many seeds that don't also correspond to some actual match you want to output. And unfortunately, we have no guarantee about that. You can easily come up with a bad instance, at least a very degenerate one. You could say the text is just all A's. And the pattern is almost that, but it starts with a bunch of non-A's. Now say if we fix K to be, I don't know, 2. So we're allowing 2 mismatches. I'm going to be mean to not have any. I start with 3 B's. And then I fill it up with A's. Like this. So I'm going to break my pattern into these triples here. I'm going to find a ton of matches for these triple A's, but none of them can possibly lead to an actual match. So the algorithm finds n times k matches or seeds, but they're all spurious. So in the worst case, and this is the number of matches. You have to check each one, so the running time is n times m. It's back to the brute force version. So this idea that I sold you as the practical solution to this problem has a really, really bad worst case. But it happens to not occur so much. I couldn't come up with an equally bad example that's not equally artificial, say. If you think about biological data, there's all sorts of weird things happening, but in terms of long repeats and so on. But there's so much self-similarity is rare. And this seems to be what kills the algorithm here. So the worst case is bad, just as bad as the brute force method. If you believe that your data is more gentle to you, then these are rare and you can get by with much less running time. At least what we can say about this is that it's not missing any matches and it returns no wrong matches. It's still an exact or correct algorithm. It's just that the running time, we don't know how to bound better than this uninteresting brute force bound. But in that sense, the heuristic part is just about the speed up. Now we can also take the same idea, finding seeds of very similar parts, in this case exact matches, and try to extend them in a different way. This picture I had on the previous slide here, that assumed, I'm just counting how many mismatches I have. I could also start now building the dynamic programming matrix of a local alignment left and right. I'm still going to restrict the segment of the text I'm going to look at. Now, say if you have, okay, let me draw this properly so that it's not just this side remark here. This is the entire text, and here is a snippet of my pattern that I found exactly matches the text at this part. I can try to extend this to, say, an edit distance at most k match. Yeah. Well, the k means I can have at most k gap symbols ever in my alignment between the pattern and the text. So the pattern will continue in some form and the text continues a bit. In the worst case, I might have k gap symbols somewhere here. So I'm using from the text, maybe it's a bit hard to write because I didn't give this a name. Say this position is J prime. That's the starting position of this pattern snippet. J prime up to, I have a name for the length. It was T before. Like this. Then this is covering J prime characters in P, and we don't have to look at more than J prime plus K in the text. If I go further left, there's no way I can get rid of all those text characters within edit distance K. And same for the right, as it's M minus j prime minus t plus 1 minus plus k, something of that sort, the number of characters to the right of that endpoint, and plus k again. So I can take a substring of the text that is essentially m plus 2k characters. And then I can find the best alignment between t prime and p. And the cost for that is essentially bounded by m and k. It doesn't involve n. So the seed helped me to make this cost much, much more local. And it doesn't even matter all that much whether I'm extending it just with k mismatches or an alignment. It's a factor m, right? If I do it like this, the running time would be m squared plus k. So that's the good thing about this idea of having seeds for matches, that you can extend them now also in a more general sense. Now, unfortunately, this will find the best possible alignment locally, but there might be alignments that are good overall. So good alignments between p and a substring of t that don't have any good enough seed. Just because they're globally good, but they're enough spread out. This is a bit harder to avoid with the general alignment scores anyways. So in full generality, this idea is then also heuristic in the sense that it might miss some occurrences, or if you tune it so that it finds all, then it might spend more time. That said, this is what many of the practical search tools are built on. They often don't just do snips, so mismatches, but rather try to do local alignments. In particular, there's two tools which are not targeted for read mapping, but rather you found in some sample taken from some environment, you found some snippets of DNA or a protein, and you're trying to find what kind of known sequenced genomes of certain animals or other living beings match this snippet that you found. And for that, a local alignment, not a semi-local alignment, is often more helpful. But by and large, they're trying to solve a similar problem. You have a pattern, you try to find that matching in a much, much larger string or a database of strings. And they use similar approaches that have a seed. I'm commenting on the second part in a bit. They have a seed and they extend this to a local alignment between the two, between the matching port of the text and the pattern. You can even push the idea slightly further. The seed doesn't have to be an exact match, but you can still use exact matching algorithms in the following way. If you restrict yourself to fairly short seeds and fairly tight thresholds for how much the seed is allowed to differ from the matching part of the text, then you can just pre-compute all possible strings, all ways to modify the pattern, so that this modified pattern and P are within distance sigma according to your alignment score, whatever score you use. That's, in general, an exponential set. The longer P gets, I think K here was not a good choice because this is, let's say T. K was the number of mismatches all the time. This set of strings P prime will grow exponentially with T at least. So it's not feasible for large T, but for small T you can do it, and then you can search all those meddled with patterns exactly in the text. That's what this blast heuristic is using. And that's still the gold standard for people to search in these databases of known sequences. So they seem to have accepted the fact that this may be a heuristic in that it doesn't necessarily find all matches, but it's the thing that is fast enough to scale to the size of data sets people have. Okay, all that's left for this part, for this unit, is a quick summary of what we've seen. We spent some time on exact matching, and if you want to summarize all the different algorithms, you could say the running time is linear in n and m, which could either be the length of one pattern or the total length of several patterns, plus the size of the output, which is only relevant for AHO Corasic, where the number of matches could be bigger than the text. You can have several patterns match at the same position. But this is essentially optimal. That's the best you can do in this setup. Whereas for all of the inexact matches, we only have partial results. For k mismatches, we can do the kangaroo algorithm in n times k time after this clever pre-processing step. Or we do these more heuristic algorithms based on small seeds that match exactly. If you want to go back to the original gold standard problem, you can either pay the price for the exact solution, usually not feasible, or you can, from what we've seen so far, use seeds and try to locally extend them into an alignment. But there we have very little formal guarantees. We're not even sure we're finding the correct set of matches. And whether it's fast or not, you're relying on your assumption about the input. And I'm not aware of some formal arguments in either direction, what kind of inputs, what properties the input needs to have. But that's where we stand. Time for a break. What is that? Sí. Here there are two words. Because they're two lines. Okay. Here, there are two lines. This one. Yeah. I think all of these are just one simple. Yes. There are two. Well, it's too easy. No. Then the order is too hard. what am I doing? Are you still puzzling over the German questions? Let's hear it.
Well, the question is easy, but the reason behind it is,
Okay.
well, das ist der Mann, ein Blank, ich gerne gefallen möchte.
Dem?
Yeah.
Sure. So what's the question around it? Why is this dative?
Dem, dem. Yeah, exactly.
Right. Yeah, this is subtle. Is this a property of the verb?
Which one?
Yeah. I think it should be tied to gefallen.
That's a verb too. Yeah, but gefallen is for me, right? Yeah. Wait, what's that on there?
Yeah, can you make an example sentence, Finn, where you use gefallen with accusative? I think it doesn't work. Well, the other case, ich gefalle ihn. This is not properly. This is grammatically incorrect. Ich gefalle ihm, dative works, but accusative never works. But why? argue that.
There's so many words I don't understand. Well, by the way, there's the sentence you just told us. The one on top. Ich gefalle ihm instead of ich gefalle ihm. The N or M at the right at the end of the sentence.
So Gemini says it's because the verb gefallen always needs dative, and you just have to know that that verb likes that case. That's not very satisfying, no?
The logic we were looking for.
Well.
Okay.
So there might be a logic behind it. Yeah. You can contrast it to other verbs like sehen. Ich sehe ihn. There it's accusative. There's different. But why? Why is that logically a difference?
Beautiful question.
Okay, so Gemini claims the difference is that ich gefalle ihm, it's about the person. And ich sehe ihn, you're essentially treating the other person as an object that you see. It doesn't matter that it's a person in this case. Whereas to impress someone, it only makes sense for a person. But that yeah. Okay, whatever.
Let's talk about less complicated.
Yeah. Complicated in a different sense. At least we can clearly define what happens, and then the complication starts after that. Not with the rules. Yeah, apologies to Finn. I think you've seen some of this in efficient algorithms. If not, it's a good refresher, like if you forgot. Have you seen suffix trees? Seen or this longest common extension problem? that I mentioned in the last thing as a black box. I think it's really beautiful. It's not super well known. Yeah. It might end up getting kicked out of efficient algorithms again if it's covered elsewhere, where I might really reduce the time there a bit. Oh, separate discussion. Yeah. There's many modules where this kind of topic fits well, and efficient algorithms is full enough. Okay, especially for this module, suffix trees are very well suited for solving some of the problems we've discussed, and indeed others that we haven't discussed yet. And maybe it's a good opportunity to discuss them. In the next unit, we'll look at suffix trees and the related suffix arrays as well, as a means to improve upon what we were able to do with exact and inexact matches, basically by exploiting more explicitly a pre-processing step on the text. That's what we'll look at. The basic idea is quick to explain, but what we'll spend some time with is cracking open some of these black boxes that we find along the way, where I first tell you why something is useful, but then there's some complexity hidden in the parts that we then still have to look at. The context, as I just said, is we're still looking at the read mapping problem as the overarching application in bioinformatics that we're targeting. And so far, we've essentially tried to be smart with the patterns or the individual reads. And well, it's time to make use of the fact that the genome, the reference genome, doesn't change all the time. So we can spend quite some thinking on this once and for good if we can speed up things afterwards. That's going to be the goal. And the first thing that we'll use for doing that are suffix trees. So let's get there step by step. We talked about tries already in the last chapter as the starting point for the Aho-Korosik automaton. So this, I think, is the same as on that slide. I just put it there so maybe you remember. It's called a try, even though it comes... Such a useful feature. Too smart. Yeah, so now you can see it again. In general, tries are just a dictionary for strings, where the keys are strings. And you can do all sorts of things with them, whatever you would do with a dictionary or a symbol table. Here, we'll always be happy with the assumption that the strings are prefix-free. This is different in the Aho-Korosik automaton. There we cannot assume this. But for this chapter, you can assume that we're always storing strings that end with some unique symbol that marks the end of the string that doesn't occur anywhere before. And then you always have this guarantee that they're prefix-free, so that no string is a proper prefix of another one, because that would mean aligning this $sign, the end of string sign, with some non-end of string character. Another way to get this, by the way, is if all the strings have the same length, and then also they can't be proper prefixes of each other. That's literally the example from back then when we talked about Aho-Korosik. This was fine back in the day, or last week, for what we wanted to do with Aho-Korosik. But you may note that there are some internal nodes in this example, also along these lines here, that are not really serving a good purpose. They're only there to make the string along the path longer, but they don't serve a purpose in separating the strings that we store further. They're unary nodes of a single child. Now, that means we can store the same information with a bit less space, and that's going to be crucial for the next step. So if you don't find this enticing for this example with just storing a random set of strings, give me a minute. You can still see it as kind of a general optimization. We can get rid of all these unary nodes by just short-circuiting the edge. Instead of going to this intermediate child, we directly go to the next node. But that means I'm now forgetting that there are several characters here. So I have to do something about that. And what I do is that in each node, I'm storing the index in the string that I'm accessing at this point, and the edges have labels that correspond to that character. For example, the root always has the 0 because there's the first character that we read from all the strings. We start at 0, remember? All indices start at 0. Now, if you follow down this right path, we skip the index 1. The next branch here is looking at the character at index 2. And if you take these two strings, BBB, BBA, you see they're the same on the first two characters, as is the third here. There's nothing that starts with BA. So that's all we do. This has one good consequence, namely there's no unary nodes anymore. By definition, we've gotten rid of all of those. So all the remaining nodes in the tree or in the trie are at least binary. And that means you can bound the number of internal nodes that we have. With this usual kind of, it's a similar argument as you've used in the tutorial, the first problem for this week about the graphs with degrees, the handshake lemma. We'll discuss this in the tutorials briefly next week, but the point is all these strings eventually sit in the leaves. They have one edge going up, and this edge going up has to go into some node. Every internal node I have has at least 2 coming in and feeds one more up. So they always reduce the number of open edges by 1. So after adding at most n-1 nodes, I'm out of edges that point further up that I could attach to another node. So in short, the number of internal nodes, or the number of nodes including the leaves, is linear in the number of strings that we have. The number of nodes on this left is also linear, but in the length of the total length of all strings. Okay, important difference. Here it's the number of strings, here it's the total number of characters in all strings. Maybe worth like, do we have notation for this in this chapter? Maybe not. Okay, that's the good news. The compact trie is indeed smaller. The bad news is I'm skipping over some characters, so I have to pay attention when I use this for searching. For example, if I look for the string BAB, I'm on this side potentially misled that if I check index 0, I'm happy to find a B. Then I'm checking index 2 and I'm happy to find a B. And so I would declare, yeah, the string's in the dictionary. But it's not actually, because it differs in the skipped character. So whenever you use search and you reach the leaf, you have to check the characters that you skipped over. That makes the code a little more complicated. It doesn't affect the overall complexity of the problem. The big O class is still the same. I can still, and maybe this is worth pointing out, search any pattern in a trie of arbitrary size in time linear in the length of the pattern I'm searching. I only did as many comparisons as this guy has characters. I cannot do more. And that's true in both the representations for tries, but in particular, it's still true in the compact trie. This is a property we'll use over and over again. Okay, simple use of tries would already be an inverted index when you have words over a text. You insert all the words of a text into a trie with a reference where they occur. And then you can search in the trie in time proportional to the length of the searched string and completely independent of the size of the web, for example. Now we go one step further. And at the first moment, it might seem this has nothing to do with tries. Let me first motivate why what's coming now is indeed powerful. And let's look at this problem of the longest common substrings. You're given a set of strings and you try to find a long substring that occurs as a substring in all of these strings. For example, with two substrings here, you can try to find the longest substring that occurs in these two words. What can you find? I guess it's fairly simple because there's only there's so much live. There's only one occurrence here, even though there's this f here. So you can extend that, and you can extend it to the a. So alive occurs in both. And that should be the longest. There's, I think, nothing else. So it's in particular a substring, not a subsequence, right? It's contiguous. Now you could think about how quickly you can solve this problem. I'm going to tell you a solution that's linear in the total length of all the strings. So just summing up all the characters. That's the same time as reading all the strings in up to constant factors. And that is not so clear. Like without some trick, this is not going to work. Indeed, there's a quote. So Donald Knuth, maybe you know from, I don't know, I think he wasn't mentioned in this module. As the author of The Art of Computer Programming or the author of Tech, a famous founding father of many theoretical computer science topics. He conjectured in the 1970s that this precise problem may not have a solution in linear time. And with suffix arrays, it does. I haven't told you what these are, but they're essentially a way to solve this problem and many others in linear time after pre-processing. So you read the strings in. Building the suffix tree takes linear time and costs linear space. And based on the properties of this tree, you can solve lots of string problems of the sort that this one exemplifies. And maybe the fact that a now famous person was wrong about the possibility there shows you that it's doing something interesting. So what is the suffix tree? It's actually not a complicated thing to define. The tricky thing is just this part, namely that you can build it quickly. That's the non-trivial bit. A suffix tree is nothing but the compact trie of all suffixes of a text. So you take the text, every possible starting position, and you read from there on till the end. Here and for all of this chapter, we'll always assume the end of the text is marked with this end of string symbol $. That doesn't occur anywhere before. And so we start with a text that has n characters, 0 up to n-1, and then the nth position is set to this $ symbol. So there's an example for this. Here's a text, and there are all the possible suffixes, including the one with just the $. And then you can just insert those into a trie. And this is already the compact trie. As you can see from these edge labels here, there's several characters along this edge that in the computer would actually look more like this, where you have these indices and just the first character as the label on the edge. Now there's another thing we can do, because this is all of the strings that we store are suffixes of the same text. We can store the text once and replace these strings with just a starting index. Then I have implicitly everything I need. If I want to know what the string is that starts, that belongs to this leaf, I know starting at 3 and reading, that's going to be the string. And that's also what you can find here if you read from the root. However, remember, what it really looks like to the computer is this. So there are some parts here where you're skipping over characters that wouldn't be represented as edge labels. So you need to store separately the text somewhere. But we don't have to copy the text in all the leaves. These are just indices, a single number. Okay, for all the explanation on the slides, we'll use this representation because it's more intuitive to work with, where you have the entire string on the edge label. But remember, for the implementation, this is what we really store. So the number of the space of the data structure is one word, one integer for each leaf, one integer in each internal node. We also store the tree structure with pointers somehow, and one character per edge. All of this is linear space in the length of the original text, if I'm generous and say words of space, under the assumption that the alphabet is not obscenely big or so. We'll not worry too much about how the suffix tree itself is represented in or tries in general are stored. If the alphabet were big, you'll have to think about how you do this if there's tens of thousands of options. If the alphabet is really big, you might have to think about how to represent the child pointers. We'll not do that basically because in bioinformatics, the alphabet is either 4 characters for DNA or maybe 20 or a few more for protein, but it's not going to explode. The number of characters is going to be fine. So in the simplest case, certainly for DNA, you can assume that every node just has 4 child pointer slots, and these can either be filled and that child is there, or it's a null pointer. If the alphabet is huge, that wastes a lot of space because of all those null pointers, and you can start to think about how to avoid that. We're not going to do that once because the alphabet isn't so big, and second, we'll in the end get rid of the entire tree anyways. This is the final outcome will be a different data structure. So we can allow ourselves to ignore that fact for now. Oof, okay, so that's suffix trees. It's a simple definition. Just take a text and all the suffixes, throw them into a trie. The tricky bit, as I said, is how to construct this efficiently. If you were to insert one of these suffixes after the other into a trie in the natural way how you would do this on tries, then you take essentially constant time for each inserted character. But the total number of characters is quadratic because you have lots of long strings. The first half of the suffix, of all the suffixes, have at least the second half of the characters. So there you go, your n squared already. And of course you can compute this precisely. So that's not going to work in linear time, and there's no hope to do that if you do one after the other in this way much faster, because the intermediate trie that you would get from building the trie just has this size. That doesn't work. Now here's another magic black box that we'll eventually look into. You could do this in linear time. You can build from the text the suffix tree. From what I described, think about the alphabet as constant. That's good enough. And you can do that in constant time in the linear time in the end. There's actually different algorithms known for doing this. I'll show you one, but there's several others that are fundamentally different. It's a problem that people spend quite some time thinking about because it's so relevant in these applications. And so they came up with some interesting ideas along the way. It started as a mostly theoretical result, but is now routinely used. Not exactly in the form that you build literally the suffix tree, as I said, but conceptually the problem that you solve is the same. So for the moment, we'll just assume that these are already here, and we'll first explore what we can do with them. At least the simple applications we can still cover, and then we'll continue next time with also some applications that don't make it into efficient algorithms. Okay, still not busy on the YouTube stream. Let's see a few examples of how we can use suffix trees for some string problems. Just as a quick reminder, what the suffix tree will really look like. I'll denote this by this calligraphic T because the normal T is the text. What's really stored is this compact trie, but you will think about it in this way. And the only difference is that we have to think about these extra comparisons with the characters we skipped that we have to do. Another kind of technical assumption that just makes some statements a bit easier is that every internal node has a pointer to the leftmost leaf below it. And in this case, it's always just the left child in this example, but that's because my example is too small. In general, it could be that some node has a long path before there's a leftmost a leftmost leaf, and then this pointer might jump over a long branch. I wonder if we always have the dollar edge though. Well, this one shows that the answer is no, right? It's just a property of the small example that here it looks like you always have from each internal node an edge to the dollar, but not every prefix is a suffix. It's not in general true. Okay, these pointers we'll just assume are there. It's easy to fill them in a linear time pre-processing over the tree. But it's convenient to assume they're already stored. Okay, I try to get rid of most of these occurrences, but maybe for saving space, I sometimes still use TI for the suffix starting at I. So let's see applications. The first one is finding a pattern in a text exactly. So the very problem we've spent a lot of time thinking about last week and earlier today. We can also solve that in a suffix tree. And the running times are a little different. First of all, clearly a pattern occurs in a text if it is the prefix of some suffix. Why is that? Well, if there's an occurrence here, I can start the text here, and then the pattern is a prefix of that suffix of the text, which means in the suffix tree, I can search for my pattern starting at the root, and then I'll eventually get to some point here where I've read all the pattern if it occurs. And I can try to find from there the starting point of this match. That's the idea. In more structured terms, what you do depends on how the tree and the pattern continues. You start at the root, and there's different options of what can happen. One option is that we get stuck and cannot continue reading with the character that is in the pattern. So, for example, this first string here, if you read A, N, and then another N, there's no outgoing edge for N. So here I'm falling out of the tree. That means I couldn't find any occurrence because there's already a prefix of the pattern that doesn't occur anywhere in the text. Then P doesn't occur. There's a subtle version of this, which is if you're inside an edge and you fall out of the tree. That happens with this second example. Here you would say BA is fine, but then this N, I'm falling out of the tree. Now remember, this is different for the algorithm because it wouldn't actually see the A and N. It would only find out after getting to some leaf and checking the characters. But you can still check it. That's one of the cases if we fall outside of the tree inside an edge, conceptually. This is one of those places where we might use the pointers I introduced earlier. You might at this point jump to the leftmost leaf, read the characters from the suffix, and you could immediately check here whether the characters match or not. It's one way to do it. Another option of what can happen is that we run out of pattern. So we've read the entire pattern, but we're not at a leaf yet. That could be this one. So you start here, you read A and A. Now we're stuck at some internal node, and that's a case where the pattern occurs, namely in all the leaves that are below this point. In particular, if you want to find a first match, or well, one match, we can again follow this dotted point, this pointer to the leftmost leaf. Then that position 3 is the starting index of an occurrence of that pattern. So again, I can find this one in constant time. At this point, I might have to check if I skipped over characters, if they actually match. I only have to do this once though. Either they match for all of the leaves here, or they don't match for any, because they're all the same in the leaves here. There's hypothetically another option that we run out of tree. This can't really happen with $, but in principle, it's another option. If you think about the case distinction, it could also happen that you reach a leaf and the pattern keeps going. Because we assumed that the $, doesn't occur in the patterns. Well, I'm telling you now, it's not on the slide. Then this doesn't happen. Yeah, I think the subtle case is what's mentioned here. You could, in this case, you have this lovely condition. If you just compare the first character, you would follow down this edge because the B matches. Then you skip 2 characters, and you would take the A and go down here. And then you're skipping over a whole bunch of things. And you would essentially run out of pattern because you don't continue with the characters in the edge. Now, in an implementation, you would find out by checking the characters. Now, the cool thing is finding the first sum match. First here doesn't mean leftmost in the text. There's no guarantee of that sort. Or returning there's no match. That is linear in the length of the pattern if the alphabet is constant, because we can just go down the tree character by character. If you want all the occurrences, that's also possible by walking through the tree and reporting all the leaves. As a last thing, let's have a look at this problem we started with in a slight variation. This is not exactly the longest common substring, but rather the longest repeated substring, which means given a single text, what's the longest string that we can find twice in the text, where it occurs at 2 positions, starting at I and at J, where these are not the same. Indeed, this is something you could use for compression, but we haven't covered this. Sorry for the reference. If you don't use suffix trees, it sounds like you have to check all substrings. You could say, I'm checking all possible substrings. Do they occur more than once? But there's a lot of substrings. It's a quadratic number of substrings in a text. So that's not going to work. Even if you were to use the suffix tree to check if they occur more than once. That, by the way, is easy, right? Checking if something occurs more than once is finding it in the suffix tree and looking if there's more than one leaf below it. But there's a lot of substrings. So how do you know which ones to check? This is again something where the suffix tree can provide us the answer. Every internal node, by definition, is labeled with the path from the root to that node is labeled with a string that occurs twice, at least. because there's at least 2 leaves below it, otherwise it wouldn't be there. It can only be a node if it's more than 2 children. That's split here. So every internal node is precisely a string following from the root to here that occurs at least once, at least twice. It could occur many times, like the A here. And the cool thing is this is an if and only if. If any string occurs twice in the text, the suffixes starting at that occurrence share a common path and then split. And so they share a common path and then split means there's an internal node. So precisely checking all the internal nodes, or the strings that lead there, will find the strings, the substrings that occur more than once. And indeed, if we're just looking for the longest, we don't even have to report all of them, just the longest. How do we do that? That's the length of the string from the root. And this happens to be stored in the trie anyways. This is precisely the numbers that the compact trie has to store anyways. It's otherwise known, I'll skip that in the interest of time. It's otherwise known as the string depth of a node. Usually we think of depth in a tree as the number of edges you have to go down, but here the edges somehow have different weights, right? Sometimes I'm doing 3-character jumps or whatever number, and other times it's just a single character. So indeed, this node and this node are both deepest in the tree, even though this needs 3 edges and this is a single one. And the 2 strings that are labeled here on the path, ana and ban, are the 2 longest repeated substrings in this banana ban. And you see that there's a quirk with this definition or with this data structure, in that ana occurs twice, but is an overlapping occurrence. The suffix tree is happy with that, and if you want to not have that kind of recurrence, it's actually a bit harder. But you can, of course, find it out by taking the difference between the leaves. Ban, for example, here is a non-overlapping occurrence. So finding these longest repeated substrings, you can essentially work out from the suffix tree. Once you have that, the string depths of all the nodes, you could compute them in a traversal, or you could observe that the compact trie has to store these numbers anyways. So they're already there. And then you just find, in another traversal, find a node with the largest number. That's easy too. So in linear time, you can solve this longest repeated substring problem. And that's very close to this original motivation problem. But let's start there again next time. Thanks, guys.